When we talk about appending, we always want to put this in terms of, does the container, does the thing I'm adding to grow easily or not? So let's talk about it. Does it grow? So in pandas, we used to have a .append method on both our series and our data frame. These have since been removed because it is an anti-pattern. It's something that you don't want to see in your code. Now, I have seen code even with the removal of .append. I have seen code that looks very much like this. We'll take a data frame and we'll end up just calling concat right on that data frame every single time. And it ends up being quite expensive in this case. And so we can reason about this in this fashion. Series.append or concatenating multiple times to a series is not a fast operation. Now, the Python list will be faster in this case, right, for growing objects. What we want to see here is actually not the appending, right, to a pandas series or a pandas data frame, but we want to grow our Python list because they are designed for that. So what we can see here, what we can reason about here is I should not be calling series.append. Thankfully, you can't anymore. I should not be calling dataframe.append. Thankfully, you can't anymore. But what you should really avoid is calling concat in a type loop in this fashion. So I've seen code that looks like this, right? I create an empty data frame and then I repeatedly append to it. Or in more modern pandas, I have seen this since the removal of append, and I had to share my displeasure with that user who I saw using this code. But we see that if I just look at I have 10 data frames in here. If I look at all 10 data frames and I read them in and I continuously concatenate to an empty data frame, well, I see reduced performance than if I had just read them all into a list and then just concatenated all of those parts. So when we're calling things like .append, we want to make sure that we are using this on containers that can grow easily, like the Python list or the Python dictionary. In fact, a fun trick that I like to use, if I want to keep track of all of these parts, I'll actually map, right, the stem of the path to the data frame itself. And you can see here, I automatically get, right, my keys as part of my multi-index for my resulting data frame. So that's a fun trick that you can use for reading in multiple data frames. Let's talk about what we can do with this, though. We don't often see, right, concatenating in tight loops, and when we do, it's a very obvious anti-pattern. Let's talk about using .lock to actually append, quote unquote, values to our data frame. I've seen this a number of times where I want to iterate over some amount of values along my index in order to keep incrementing it. And so I'll show you what the goal is here. I have a data frame that has 3 rows. I want to add 200 more rows of dynamically generated data. In order to do that, yes, I could use concat, or if I have an older version of pandas, I could use append. But what you can see is I'm using .lock, and I'm using .lock to actually create a new index position that is not currently being used. And so I'm just adding more rows by using .lock here. And so let's see how long it takes for us to grow rows. To add 200 more rows to this data frame using .lock, well, it takes me a little over 1/10 of a second. Contrast that with how long it takes me to add 200 columns. And you can start thinking, data frames are designed to grow in terms of their columns. Adding a new column should be a cheap and fast operation. In fact, the data frame in its very, very, very early days was kind of like a fancy wrapper around a dictionary that just pointed to a bunch of NumPy and D arrays. And that way you could just use dictionary accession to grab a single column or a single array out of your quote data frame at that time. It has since become much more complex, and we'll talk about that in just a moment. But adding new columns to a pandas data frame, cheap operation. Adding new rows to a pandas data frame, expensive operation. We need to reallocate all of our memory. We need to increment it by 1, allocate that plus write a new slot, or however many new slots we need for the contiguous underlying arrays. And then we need to copy over the old data in place of the new data. And we're doing that every single time that we call a .lock that requires an insert and not an update. So that's the story of pandas data frames, right? Expensive to grow rows, cheap to grow columns. Now, let's talk about it in this fashion. If I take a pandas data frame and I have a column of letters, I have a column of integers, and I have a column of floating point values, well, we can actually take a peek under the hood. If you've never inspected the underscore data attribute, we get access to something called the block manager. Now, what I told you was that earlier, the pandas data frame used to look like a dictionary. It still kind of does look like a dictionary, but it's a little bit smarter. It takes all of the columns that have the same data type, and it will try to store them in the same array. And so what this means is this. If I want to add a new block, you can see here my object block, this corresponds to my letters. My int64 numeric block, this corresponds to these integers, and my numeric block of float64, well, this looks at my floats or contains my floating point values. So I have 3 different NumPy and D arrays here backing this pandas data frame. If I create a new column, pandas doesn't say, okay, well, I'm going to take the existing numeric block that has an int64 data type, I'm going to expand that to have a new row in it, or a new column in this case. Instead, it has a very cheap operation. This is why adding a new column is so cheap. It just appends another numeric block to the block manager, right? This block manager is designed to grow. It's kind of like a Python list in this case. And so we can keep adding columns very cheaply. But you can think if we add another row, we have to resize this block, we have to resize this block, and we have to resize this block. So that's 3 different NumPy and D arrays that we need to reallocate and extend. But I can force pandas to take this new column, and I can force it and say, hey, I want you to actually examine all of your data types, all of your blocks in the block manager, and I want you to actually combine everything that is alike. This is called consolidation. And what happens when we do this is we just get a denser view into the block manager, or a denser view into the allocation. But note that actually calling consolidate doesn't force the data frame to consolidate. It just returns a consolidated view of the block manager. I would need to rebind that block manager, that new block manager, to the existing data frame and reconstruct parts of the data frame. There are a couple rules of what will and will not trigger a consolidation action, but what I want to share with you is this. If I turn off this warnings filter on the previous cell where I was adding 200 columns, you can actually see that I get an error. I get a performance warning. Data frame is highly fragmented. This means that I have created a lot of brand new blocks to this block manager, and Pandas is recommending saying, hey, you have a lot of blocks that could be combined and are currently not combined. The more blocks you keep adding to this thing without combining them, the worse our performance is going to be. And so let's go ahead and we'll take a look at that very shortly here. But what I want to share with you about this is if I perform a simple operation, let's take a look at this block here, data. You can see I have numeric slices, right, all the way up to 200. We clearly could benefit, and they're all int64 type, we could clearly benefit from consolidating this view into, right, a dense NumPy and D array. So what can force that? Well, it turns out if we copy our data frame, this triggers a consolidation. And now if I look at this block manager again, now we only have one int64 type block, but we can see that the slice is now 2 by 3, right, instead of 1 by 3. And I'll differentiate that, I'll comment that out, right? It's 1 by 3, and when I leave that back in, it's 2 by 3. So we can think about how Pandas is actually manipulating or using NumPy to back all of the columns on this data frame. Now, let's take a look at how we can use this knowledge to make sense of some Pandas operations here. If I use that previous approach of appending or adding brand new columns to my data frame, we see that I end up with a very highly fragmented, right, block manager here. Whereas, and this is that same approach that you saw earlier, whereas if I create a temporary data frame that just contains, right, all of the series that I have, when this data frame right here is being constructed, it will consolidate all those blocks for me. Then if I want to add that to my existing data frame, I can just call it .join. And when we do this, we actually end up with a fairly marked performance difference. But this is not the only time that you pay for the performance difference here. The next time I do an operation, say I want to do a .sum, it's much easier for pandas to look at a single, right, N64, say, 2D array and call .sum on that, right, with axis equals 0 and let NumPy perform its own vectorized operation. With the block manager, we have to understand that when it's fragmented, we're going to be hitting a Python for loop, and we're going to be going to the first N64 block, then the next one, then the next one. We're going to do that 200 times. And so by calling .sum, right, we're going to dispatch those methods. And you can see with my fragmented block manager here that I am paying a price of having not consolidated my view into memory, meaning I have a very slow .sum performance compared to the consolidated view, right, df2 in this case, which has a consolidated view of memory. And let's revisit what those look like. Block 2 just has 3 individual blocks, but we have, right, our N64 is a 200 by 3 ND array, whereas block manager number 1, right, has 200 separate blocks in it. In fact, if we force a consolidation outside of our sum timing, this is when we see a huge gain in performance. We can actually see that these are starting to approach each other. And the more I run this, the more likely, right, we're going to have the same performance. And that's because the consolidation is very, very critical to working with many columns of the same data type. So if you have a fairly wide data frame, you want to be taking care of this block manager and making sure that you're not arbitrarily adding columns. But the next thing I want to share with you is we can add columns, yes, but what if we want to update existing columns? Well, it turns out there's a few ways that we can do this. We can update an existing column by simply using the .assign method. And when I use the .assign method, you'll see this approach a lot. I see this on Twitter actually a lot. You'll see I use a dictionary comprehension to loop over all the existing columns in the data frame. Then I'll do something with those columns. Maybe I'll demean them in this case. And then I'll map that back to the column name, and I'll unpack that into .assign in order to override the existing columns. This is a neat trick if you want to do both updating existing columns and adding new columns, but do take care that this is not necessarily going to result right in that consolidated block memory. And you're also paying the price of this. You're paying the price of constructing a bunch of series, throwing them into a dictionary, unpacking them, and then taking all those series, form them into a data frame. We're actually assigning them to the data frame one by one, and then working with your resultant structure. Whereas if I perform a direct calculation, right, this is going to be the fastest here, and I'm not updating anything in place here, so to speak, and so I end up creating a copy of my data frame and storing that out. If I simply create an explicit copy and then I loop over these structures, we can see the performance difference, especially compared to that dictionary comprehension approach. I can loop over the columns of the pandas data frame quite cheaply, and I can operate them on each of them quite cheaply as well. And so for this approach, I avoid the overhead of creating, right, an intermediate bunch of series inside of a dictionary, and instead I can simply update these columns in place so my garbage collector can run and actually free up more memory for me. And so we see a little bit better performance here. The last approach that I might do is if I want to truly update something in place, you can use the update method. And here I'm just creating a new data frame full of the values that I want to update and then updating those original values in place. And so here you end up seeing that, right, we have pretty much the same performance between an explicit copy and an update and just iterating over these columns. So we can think that implementation actually might be quite similar under the hood. And so when we talk about iteration in pandas, or appension in pandas, I should say, is we want to recognize that pandas data frames have a very fast ability to add new columns. It does not have a fast ability to add new rows. But if we are adding a bunch of new columns or updating existing columns, we do need to take care that our data frame, the memory representation, does not become too fragmented, because that could very severely impact our performance on operations that should be fast otherwise. Pandas has a lot of abstractions, and we want to take care that the underlying implementations are being called as efficiently as we can allow. And just understanding a little bit of under the hood in pandas can go a long way for us.